In the last class, we learned how to use off-bound built-in up method to feed the electrons into the orbital of a specific atom. For example, how to do it? First, if we do building up into potassium, so we look at the periodic table, we found potassium has 19 electrons. And then we follow that sequence we learned before to fill in the electrons from the low energy orbitals to higher energy orbitals. Yeah. Which means we put 2 electrons into the first orbital, has the lowest energy, 1s, and then we continue with 2s, because s orbital only can hold 2 electrons, like we talked about in the last class. And then the p orbital can hold 6 maximum, and we continue. Because we have 19 electrons, we have to calculate, okay, now we have 10, I put 2 here, 12, 18, that is 19 electrons, then we finish. So this we call it, we call this electron configuration the 4 spectroscopic notation. That means we write down everything. This is why we use a 4, okay, 4 spectroscopic notation. Use the same method, we can do the off-bound to the argon. Again, we look at the argon from the table. Argon has 18 electrons. Of course, we use the same method, and 1s2, 2s2, 2p6, 3s2, 3p6. Then we finish, because argon only has 18 electrons, right? Then let's compare. You will find this part is exactly same as that part, identical. Of course they are same, because 18 electrons, yeah, it's 18 electrons. The only difference is for potassium K, it has 1 extra electrons, yeah, filled into the 4s1 orbital, because potassium has 1 more electron compared with argon. So in order to save the paper, save the space, makes our life easier, why not, when we write the potassium electron configurations, how about we write it this way? We put argon here plus 4s1. The reason is this part is exactly the same as the argon electron configuration. So in order to save the time and energy, we can use argon, use this bracket and argon to replace this part. Yeah. So when people see this, people will say, oh, you have argon here. That means you have this, all this, plus these ones come from here. So this is called a noble gas core notation, right? It's much shorter, right? So similarly, we can do others like sodium, for example. You have 11 electrons, but Ni has 10 electrons. So that means you can write down the first 10, that means this part. This is for Ni. This is the electron configuration for Ni. And then we add 1 more electrons after this bracket. Yeah. Similar like any others, like aluminum, we always can write down the first 10 replaced by this one. Yeah. So these all are called a noble gas core notation. The reason we call it noble gas is because all these writings, they use this noble gas electron configuration to replace the inner part to save the space. And there's some extra part we just leave it outside of this bracket. Yeah. So an electron in atoms outside of noble gas core, we call it valence electrons. Yeah, like these electrons. This is in noble gas core, and these electrons we call them valence electrons. So these valence electrons are primarily involved in chemical reaction because elements, they tend to form the noble gas core configuration. That is stable because when the electrons are the orbitals are completely filled by electrons, they are stable. So after they lose these upper layer electrons, they have this noble gas configuration. We call it noble gas just because they are inert, don't like to react with other elements. Yeah. So okay, anyway, this is called valence electrons. Yeah, we learned the rules like this, right? All filled in previous I showed you. But we also should know there are some exceptions. So this slide gives you two very typical examples. Exception to off-bar principle. The first is chromium. This one has 24 electrons. If we follow this sequence, let's see, 1s2 to s2 to p6 10. Okay, 3s2 3p6 4s2 20. We have 4 electrons. We should put this 3d4. So this is if we follow the off-bar principle we learned from last class, this should be its electron configuration. However, in reality, from the experiment, its configuration actually like this. Yeah, so when we do this building up, we only fill in 1 electrons on this orbital, and then we put 5 on this orbital. So why? The reason is because, okay, this is based on experiments. It's not based on our favor. But we developed some theory to explain why. So the half-filled 3D subshell are more stable. So this is the reason. In order to make it stable, to make the overall energy lower, so these electrons actually goes to here. Yeah, to make this one half-filled. Half-filled, what it means? Totally filled, this one should be 2 electrons for each one. You should have 10, right? But now each one get half of the 2, that means 1. Each orbital get 1, yeah, half of the maximum, okay? So this is stable. Similarly, for copper, we have 29 electrons. If we follow the sequence I showed you in the beginning, at the beginning of this lecture, so we should end up with this 4s2 3d9. Yeah, should be 9 electrons on the d orbital. However, in reality, copper 3d orbital has 10 electrons, and there's only 1 electron on the 4s orbital, like this. Okay, in short, this is reality. This is according to the off-bar principle, theoretically. Yeah. So again, we use similar explanation. This happened like this is because completely filled 3D subshell is more stable. For example, this one, 3D orbital maximum can hold 10 electrons like this. Each one filled by 2 electrons, you will have 10 for these 5 orbitals. So when the 3D has 10 electrons, that means each orbital are completely filled by the electrons. It's more stable compared with you put 2 electrons here, you add 9 electrons here. That one orbital is half filled. It's not completely filled. Yeah. So other similar exceptions, they are in the same column like the chromium and the copper. For example, copper, silver, gold, when you check the table, they are on the same column, the same group. So they have the similar exceptions. But we will, in general, we will not test this one, but I think these two are very typical and more important. You should memorize them. Okay, this slide we introduce another two new term, paramagnetic and diamagnetic substance. So what is that? So paramagnetic substances are those that contain net unpaired spins and are attracted by a magnet. I think two phrases I highlight by underline. Yeah, underline this one. You should pay attention. First, they are net unpaired spin, unpaired electrons. Second, can be attracted by a magnet. So I will give you some example later, but here let's finish the definition first. So the diamagnetic just opposite. That substances are those that do not contain net unpaired spin. All are paired, in other words. Because they all are paired, so they are not attracted by magnets. Or you can see they are repelled actually by magnets. Depends on the polarity. So examples like this. For lithium, there are 3 electrons. Using the off-bar principle, we fill the 2 electrons into the lowest energy orbital here, and then the third electron go to a relatively higher energy orbital, 2s1. You see this is unpaired. This is paired. Paired means you have 2, right? Yeah. But here is unpaired. As long as there's at least one unpaired orbital, we call that substance, the whole substance is unpaired. So that substance can be attracted by a magnet. Let's look at the Ni. Ni has 10 electrons. Follow the building up method we learned before. That 10 electrons will be filled this way. Or we can use the diagram we learned in the last class. Okay, so 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. That means there's no orbitals. There's no orbital unpaired. All are paired, you see. All are double paired. No unpaired, so their spins are cancelled out to each other. Do you remember we learned spin? Yes, we learned 4 quantum numbers. The last one is a spin, the quantum number. They have the value of positive half and negative half. If everyone is paired, okay, they have a different spin direction. One go up, one go down. That means they all canceled out. If they canceled out, that means that one cannot be attracted by a magnet. Okay, let's come back to the definition. So this we call a paramagnetic, and this is diamagnetic. So let's do some in-class practice. So is an atom in the following configuration going to be attracted by a magnet? So in order to answer this question, you simply check if they are paramagnetic. If yes, they can be attracted by magnets. So what is paramagnetic? So that means you have unpaired electrons. One look at here. They are two orbitals are unpaired. It's unpaired, this one. I'm talking about this orbital should have two if in order to pair, but we only have one. This is the same. We have two unpaired. That means this is a paramagnetic substance. So then can be attracted. Yes. Answer is A. So, before we learn the ground, we briefly talked about ground and excited orbitals. Here, let's look at the detail from the diagram. So the ground state, before we said it's the lowest energy state, and the excited state is any higher energy state, right? This is what we learned before. So let's take a look at the lithium. So for lithium, when we use off-bound, or in English, building up principle to fill the electrons into the orbital, as the principle said, we should start from the lowest energy orbital. We should start from the orbital that has the lowest energy, which means 1s2. Okay, after this one down, another lowest available orbital is 2s1. Yeah, when we do that, of course, this is a possible lowest energy. Yeah, this is the way we filled into the lowest energy. So this is why this is called a ground state. The ground state means the lowest energy state, right? You cannot make the energy lower, right? Because this is the lowest, the orbital with the lowest energy. And this one is also after this one, this is the lowest. Let's take a look at this one. If we fill the electrons, if the electron configuration looks like this, that compared with this one has a higher energy. Why? Because 2s has a higher energy compared with 1s, right? Yeah, we talk about that. The principal quantum number is related to the energy. When the principal quantum number increases from 1 to 2, the energy increases. If you fill the electrons onto the higher energy orbital, of course, overall, the energy is higher compared with this one. Okay. Similarly, like here, if you put the electrons into the 2p orbital like this, that also has higher energy compared with the 1s. So, because similar like here, if 3 electrons go to that higher energy orbital, that means they all are excited state, which means they all have higher energy. Yeah. So, okay, in short, yeah. This is the only ground state, and all others have a higher energy. They belong to the excited state. Similarly, I'll give you another example. If we use the off-bound principle to fill the electrons into the orbital, we always start from the lowest energy, right? Talk about that. So that means the first lowest energy is this one, and then another lowest energy after this one, and the leftover, we should do it this. When we do this, this belongs to the ground state, right? You can check it if you can do the any other way. Has a lower energy than this way? No. Then let's take a look at this. from the Hond rules, if you forgot, you may check your previous lecture notes. So the Hond rule said if the two electrons go to two separate orbitals, they have the lower energy. Yeah. In other words, the electrons, one filled in electrons tend to do it like this. Each orbital get one electron first before any orbital gets the second electrons. That one will have the lower energy according to the Hond rule, which means this one has a higher energy. Okay, anyway, according to the definition, any higher energy state is called excited state. Okay, this is also belong to excited state. Similarly, if these electrons go to here, it's also belong to the higher energy state, and similarly like this. If the electron from the lowest energy state go to the higher energy orbitals, they all belong to the excited state. And however, let's take a look at this. Is this excited state? The answer is no. This actually is not exist. Or, in other words, electron states that like this is not allowed. According to the Pauli exclusion principle, it's not possible to fill two electrons, identical electrons into the same orbital. In other words, it's not possible that two electrons have the same 4 quantum numbers. Yeah. If it's like this, they have the same spin quantum number. That means they have altogether the identical 4 quantum number is not possible. So that one is not allowed. Yeah, in short, according to the Pauli exclusion principle, this is not allowed because each orbital only can hold only 2 electrons of the opposite spin. That is the conclusion from the Pauli exclusion principle. Similarly, like this is also not allowed according to the Pauli exclusion principle. If one orbital holds 2 electrons, that 2 electrons must have the opposite or different spin quantum number. Yeah. In other words, if one go up, another one must go down, cannot be identical. This is why I call it exclusion. Yeah, must be different. Yeah. So okay, let's do some in-class practice again. For example, if I ask you to identify which diagram is this, is ground state or excited? Oh, it's not allowed. So according to the last slide, we talk about this one is not allowed. It's not ground state, it's also not excited state. Because for excited state, it must be possible, allowed, we can call it excited state. This one even not allowed, that means it's not exist at all. So this one actually is belong to the excited state because this one did not disobey any principle. It's not against any Pauli exclusion principle. And so this one is ground state because this one has the lowest energy. We can do, right? Yeah, it has the lowest energy, so it's belong to ground state. This one is also allowed. You see, every orbital has 2 electrons have different spin. It's okay. However, this is allowed. However, this energy is higher compared with this one. Yeah, according to the Hond rule, this one has the lowest energy if this filled into a different orbital. But you can, yes, you can fill into the same orbital. It's not against the exclusion, Pauli exclusion principle. However, the energy is still higher than when you put electrons onto the 2 orbital. So if it's allowed only have the higher energy, so this one is belong to the excited state. It's belong to excited state. Okay. So above from the above we talked about the electron configurations of ions. Here, if the neutral atoms, okay. So here, let's take a look at the ions. How about ions? Let's first take a look at the cations from the representative elements. The typical example is sodium, and sodium has 11 electrons. If we use that method, we fill in 2 electrons here, 2 electrons, 6 electrons, and then the last electron go to here. When the sodium forms the ions, this is a noble gas core configuration. We'll talk about that. It's the same as here. The only difference is use neon, which has 10 electrons to replace this part to save the space. When the sodium become ions, it loses 1 electron, right? We learned this one before. And when they lose 1 electrons, they form only has 10 electrons now after losing 1 electrons. That means that will be exactly the same as the neons. Yeah. So this is a complete, okay, this noble gas. After sodium lose 1 electrons, their electron configuration of the noble gas core notation will be this. Yeah. So, you can write it this way. Yeah, it's the same. Yeah, this one is the same as this part. The brown part is the same as this part. So the electron configuration of the sodium will be, you can write down this way for the complete electron configuration, or you can write the noble gas core notation by this way. Okay. So okay, in other words, for ions, we like the magnesium, we take a look at the table and we found that magnesium has 12 electrons. When they form ions, magnesium will lose 2 electrons. To form, that means you only have 10 now. Then the 10 electrons will have the exact same electron configuration like the neon. Yeah, this is why the magnesium ions, the noble gas core notation can be written this way. Similarly, like aluminum complete neutral aluminum has a complete electron configuration like this. After they become 3 positive ions, that means lose 3 electrons, right? One lose 3 electrons, and this 3 is gone. That means aluminum ions will become the noble gas core notation will be like this. So when you look at these 3, it's very interesting, right? So they all have the same noble gas core notation for these 3 ions. So they are all, these 3, sodium, magnesium, aluminum, we give a name, they are called isoelectronic. Yeah, because they have the same electronic, configurations. You see, these 3 ions have the same electronic configuration. This is why we call it iso. Okay, we give a name. So they all have the stable noble gas electron configurations. From here, you also can see when the elements, when their orbitals are totally, completely filled with electrons, like a noble gas, they will be stable, right? Yeah, this is why they lose these outer layer electrons, yeah, to form these electron configurations, like the noble gas, yeah, electron configuration. So they, after losing these electrons, form this one, they are stable. This is why certain tend to form 1+ ions, and magnesium tend to form 2+ ions. They will not form, they don't like to form like 3+, or because after lose these two, it's already perfect, has a perfect noble gas configuration. Why they should lose more? They will not. After they reach this configuration, they are stable. Okay, let's take a look at the ion. So ion, like we learned before, which means ions has a negative charge by gaining some electrons. Let's take a look at fluorine first. Fluorine, when we look at the table, we know fluorine has 9 electrons. If we use that method, we fill the electrons 2 into here, 2 into here, and 2p5. This is for neutral atom. For ions, you see, fluoride ion has 1 negative charge. That means have 1 more electron. That means it has 10 electrons now. 10 electrons. So that means electron configuration will be like this. Compare this one with this one. 1 more electron. Again, you will see, okay, this one is same as Ni, right? Ni has 10 electrons, has the electron configuration like this. Okay, we can write it this way for fluoride ion. If we use noble gas electron configuration. Similarly, for oxygen, has neutral have this. One gain 2 electrons, form the ions. It has this one like Ni. And okay, nitrogen is the same. Nitrogen has this as a neutral electron configuration, and then gain 3 electrons also will form this noble gas electron configurations. They are all stable. They are also called isoelectronic properties, yeah, because they all have the fluoride, yeah, oxygen, nitrogen ions, they all have the same electron configurations. So how about we talk about the main group before, like the group 1, 2, 3, like the group 6, 7. How about the transition metal or transition element? In general, we first write a configuration for a neutral atom. Then we remove the electron from the outermost s orbital first, and then remove the electron from the underlying n-1 d orbital. Okay, what I mean? Let's take a look at some example. For example, this manganese. Okay, if you follow the sequence of the off-bow principle sequence, you start from 1s and 2s, 2p. You will end up, this inner part will be same as argon, you have to save space, and with this outer layer electron, yeah. So when this manganese forms ions, it will first lose this 4s2 electrons, not these electrons. Okay, this one you should pay attention. They will not lose the electron from the because seems this has a higher energy, right? Yeah, we use a off-bar principle. We talk about that. We filled in from the lowest energy and gradually to higher energy. This one has the highest energy. However, when we lose electrons, this debate about that is different from the built-in. It loses these two electrons first. Yeah. Okay. Anyway, just memorize. They lose electron from the highest principal quantum number. For example, this one has a higher principal quantum number compared with this one. 4 is bigger than 3. We lose this electron first. 4s2 electron first. When we build in this one first, and this one last. Yeah. And when we lose electrons, this one will be loose first. So similarly, like a copper. So copper 1 plus ions. For that one, this electron will be loose first, and then start lose electron from the d orbital. Yeah, even d orbital has a higher energy. Yeah, you can think about that. Yeah. So I highly recommend you use this off-bar method to practice building the electrons into different elements. You can randomly take many elements, just follow this sequence, right? That will help you to memorize it. For example, you can do on lithium, sodium, potassium, and calcium. Yeah, why not do it? Yeah. When you do it, you will find out. Excuse me. Yeah, you will find out the upper layer of the orbitals. They have. I skip the inner part, okay, in order to let's find some general trend. Yeah. You find the lithium end up with 2s1 because it has 3 electrons, 1s2 and 2s1, right? And this one end up with 3s1. And this one end up with 4s1. The inner part I skip. Yeah, you can use a noble gas, yeah. Noble gas plus this one, in other words. And so the mechanism will end up with 3s2. Then if you look at this one, you will find, okay, 1s, 2s, 3s, 4s, 5s. They have some general trend you can follow, right? Yeah, they all end up with s1 for this group 1. And this one, group 2, Roman numeral number 2, tell you this is group 2 elements. They all end up with this s2 orbital, right? With 2 electrons. It's quite interesting, huh? And the reason why it's like that, because for group 1, you see, if we use that method we learned before, this is these electron configurations. They all have the noble gas as a core, and then they end up with this one. Yeah, this is why I ask you to do. You practice this one. You find out if it's true or not. If they are all end up with S1 or not. Yeah, don't trust others. You should do it by yourself. All have the complete inner shell and 1s electron in their outer shell. So this is a conclusion we can. So all group 1 elements are metals are easily give up the single outer shell electrons to form 1+ ions. So from here answered you why these elements like to form the 1+ ions. Before, we just tell you memorize, okay, group 1 form 1+. Now you know the reason. Because when they lose 1 electrons to form 1+, they become the noble gas electron configuration. That means stable, noble, inert. Let's take a look at the others, main group. Let's take a look at another main group. For example, this group, 3. When you look at the Roman numeral, number 3, it's group 3. And so the electron configuration will be end up with 2s2, 2p1 for this one. And if you observe, you will find the general trend is like this: S2P1, 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 S2P1. The only difference is this number change when the period, or when this is a principal quantum number, change from the 2, 3, 4, 5. Yeah. So similarly, like here, the carbon has S2P2 and S2P2, SP2P, and P2, S2P2. And the only difference is the principal quantum number increase from 2 to 3 to 4 to 5, right? This is a general trend. Yeah. If you look at the horizontally, they all have the SP, SP. The only difference is when you go right side, so the electron increase. Yeah, you see this is S2P1, S2P2, because carbon has one more electron than boron. So this is why this change from 1 to 2. And here change from 2 to 3 because nitrogen has one more electron compared with carbon. Okay, with the increasing of the electrons, this number varies until you get the noble gas S2P6. All orbitals are completely filled by electrons. This is a general trend. We also can find some general trend from the transition metal. They all have the DX XY configuration. For example, if you look at here, they have the D1S2 and D2S2 and D3S2, and like that. Everyone has one more electron compared to the previous one, but they all have the DS, yeah, DS, DS. And if you look at it in this direction, the 3, 4, 5, 6, the principal quantum number increase. Yeah, you may check it by yourself. For lanthanide and actinide, we learned before, they all have the F subshell fills with the electrons. For example, you see, this is a F1, and then filled up like F3, F4, F5, F6, F7, all F are filled with the maximum F can hold 14 electrons like this, right? Yeah. So this is a complete periodic table that filled by different electron configurations according to their groups. You see, the summary what I talked before. Okay, so you may take a look at this table. I will post this one on the canvas. So we stop here. I will stop recording.